This video is the first in a series of videos on exponentials and logarithms. Now, we will meet exponentials and logarithms later on in the course, so we'll meet part B then. So for just now, part A is just an introduction to exponential functions and logarithmic functions. So today, this video is going to look at exponential functions. So an exponential function is a function of the form f of x equals a to the x, where a and x are real numbers and a is greater than 0. So if we just examine this function firstly, as I said, we've got f of x equals a to the power x. Now, when we have powers written in this way, we know that a is the base and x is the exponent. So hopefully you'll remember that from studying indices last year. And if we have that, what we can say here is f of x is an exponential function to the base a. So let's examine what happens when we start substituting values into this. Is there anything that will happen every single time when we graph the exponential function of this form? So let's set x equal to 0 firstly. So that means that f of 0 will be equal to, now that is f of x is equal to a to the x, so f of 0 is equal to a to the 0. Now we know that anything to the power 0 is 1. So that gives us our x ordinate of a point is 0 and our y ordinate is 1. So we've got the point 0, 1. Let's set x equal to 1 this time. So this time we've got f of 1 is equal to a to the power 1. And anything to the power 1 is that thing itself. So in this case it's a. So we have 1a. And what that means is every single function, every exponential graph of this form, okay, it's not been transformed, it's just the basic exponential graph, passes through these points 0, 1 and 1a. So what do these look like then? So if a is greater than 1, we're going to have an exponential growth curve. So you can see it's going upwards from left to right. And if a lies between 0 and 1, we get an exponential decay curve. And you can see there that each graph passes through the point 0, 1 and 1a. So if we had the graph of f of x equals 2 to the x, we'd pass through 0, 1 and 1, 2. If it was y equals 5 to the x, it would pass through 0, 1 and 1, 5. If it was y equals 1,000 to the x, it would be 0, 1 and 1, 1,000. So hopefully you get the idea there. You can see what's going on. So crack on with an example. So we're asked to sketch the curve with equation y equals 6 to the x. Now you might already realise from the previous slide, yep, we've got the points 0, 1 and 1, 6. Okay, but let's prove that using algebra as well, just to be sure. So when x is equal to 0, obviously we would then have y equals 6 to the power 0, and we know that anything to the power 0 is equal to 1. So we've got the point 0, 1. If we then set x equal to 1, we know that y is going to be 6 to the power 1, which is equal to 6. And that gives us the point 1, 6. And then we are equipped to draw our graph. And we can plot our points firstly, 0, 1 and 1, 6. And that allows us to draw our exponential curve in there as well. So that's the end of the examples there. There's an exercise associated to this for today, but before you go just now, we're just going to quickly talk about the exponential constant. Now the exponential constant e can be considered one of the most important numbers in mathematics, and it's often called Euler's number, which is named after a famous mathematician, Leonhard Euler. And the number E is known to over 1 trillion digits of accuracy. So it's a bit like pi in the sense that it's not just 3.14 pi, it goes on forever. The decimal places are infinite. So Euler's number is a bit like this as well. So the bit that we know of it, or the first part that we know of it, is this. So it's approximately 2.7. And obviously then that allows us to look at the natural exponential function. So if we had the function f of x equals e to the power x, that is the natural exponential function. And likewise, if we were to draw the graph of this, it would still pass through the points 0, 1 and 1e, or rather 1, 2.71828, etc.